Okay, so this is my video number 19. Right, in this video I'll talk on the nonlinear system of the non-autonomous system. Okay, so we talk on nonlinear system. Nonlinear system for the non-autonomous system. Non-autonomous means the function on the right side depend on t. Okay, so we consider the nonlinear equation. Consider the nonlinear equation of the form that x dot a of tx plus f t x. Let's call this in this video I'll call this equation as equation number 1, where at is continuous. Where at with the element a, I, j of t, this is continuous, m by n matrix, and define on t 0 to infinity. And can you see this? I hope so. All right. And the vector function f tx, which is this is a term of vector, t x and so on, as well as x itself is a vector. Right? So, and f satisfy the following condition. Satisfies number 1, fx is continuous, ftx is continuous, for norm of x less than some number a for t 0 to infinity. And condition number 2, we have the limit as norm of x goes to 0, f tx, the norm of f tx over norm of x, this is equal to 0 uniformly with respect to t. That is for condition number 2, we can write that f t of x, the norm of t of x, is of order norm of x. See, uniformly in t as norm of x approaches 0. Okay, so this condition, condition number 1 here, ensure the existence but not necessarily unique solution of the nonlinear system. And whereas condition number 2, so I can write here condition 1 assures the existence, local existence of the solution of those system number 1. And condition 2 implies that f t0 is equal to 0, which gives us x t is 0 for t in 0 to infinity. Implies that this is the solution to the nonlinear system. Solution to one nonlinear system. Okay, so if you look at the condition number 2, you look at the condition number 2. From condition 2, we know that when x close to 0, when it's close to 0, when x, the norm of x close to 0, the system ATX plus FTX is nearly like ATX. Okay, when norm of x close to 0, the nonlinear system will look like the linear system. So therefore we should expect that the solution of if the solution of x dot ax, which is linear case, approaches 0, if the solution approaches 0, as t goes to infinity, so we should expect the same. You should expect the same for the nonlinear system. So do those solution for 1. Okay, so it is equivalently, if I can say that, if the solution of the linear system asymptotically stable, if A as is a real constant matrix. So we can say that the solution xt 0 of 1 of our nonlinear system that I gave earlier, this system, okay, is asymptotically stable, and this solution is correct. Okay, this solution is correct if, or in the case I would say A t is equal to t, which is the constant matrix. Now, relating to this assertion, I would like to give a quite simple example. So let's see this example. So we consider x dot y dot equal to 1, 0, 0 half xy plus minus x squared minus xy minus 3/4 xy minus 1/4 y squared. Okay, so this is our A. This is our matrix A, and this is the nonlinear parts. So it is clear that from that the determinant of matrix A, this is different than 0. Okay, so which means satisfy certain condition in the previous nodes. And if you find the critical point, it is not difficult for you to find the critical point. Just we have x, first line that we have to find the critical points. So you have x minus x squared minus xy that equal to 0, and the other one you have y, half y minus 3 over 4 xy minus 1 over 4 y squared that equal to 0. So if you solve these two equations, you will get the critical point. I write it here. So we get the critical point is given as we have 0 0 0 2 1 0 half half. Okay, and 0 0 here, this is the isolated critical point. Isolated critical points. Now if you look at the function, the nonlinear parts here, let's say consider the first let's say this one, let's call that g1. Let g1 xy that minus x squared minus xy. If you use the second condition, I mentioned a second condition here, this condition that I mentioned earlier, that so that condition, yeah, if you use that condition, so we need to write or transform into the a polar coordinate. So we let x r cos theta and y r sine theta. So therefore we have for g1 xy over r that equal to minus x squared minus xy over r. Okay, so this is we can use that substitution. That will give you minus r squared cos squared theta minus r squared sine theta cos theta over r. So obviously you can cancel out r there. Then as r goes to 0, yeah, so all those things will goes to 0 as r goes to 0, because this depend on r. You can cancel out r there, so we have r. So as r goes to 0, definitely everything that goes to 0. So which means the solution is what? Asymptotically stable, because when you take the limit that goes to 0, it goes to the isolated critical points. So which means our solution is asymptotically stable. Asymptotically stable. Okay, so that's ensure the assertion that I gave earlier. Yeah, if the matrix A is constant, so the outcome of that nonlinear system is that the solution of that nonlinear system behave asymptotically stable. Alright, so I hope that that's clear with that example. Now all this we can put it in a theorem. You can put it in a theorem. The proof is a little bit quite lengthy. Let's put this in the theorem. If A is an m by n matrix, okay, whose characteristic polynomial I just put it like that. Yeah, characteristic polynomial is stable. And f tx satisfies condition 1 and 2 in the above, yeah, then the solution xt 0 of system 1 non-linear system is asymptotically stable. Alright, so this theorem, the previous example I gave just to show that when A is for the nonlinear system, when A is constant metric, the solution xt equal to 0 is asymptotically stable, and this theorem confirms those examples. Now, to prove this theorem, it's a little bit lengthy, but I'll try. Okay, so the proof of that theorem, first thing what we need to show is that what we need to use is that the stability of the characteristic polynomial. What does it mean? If consider the linear system x dot equal to ax, and with the fundamental matrix, phi, then by hypothesis, because of the stability of that system, there exist some numbers such that the norm of phi less than some that number. Okay, so we first show that the solution xt 0 x naught is defined on 0 t infinity when x naught near 0. When x naught near 0. Okay, and if phi t is the fundamental matrix, phi t is the fundamental matrix of x dot ax equal to x, this is the linear system, such that phi naught is the identity, okay, then due to our hypothesis here that the characteristic polynomial is stable, so then there exists a positive number r such that r and alpha such that the norm of phi t less than those re minus alpha t for t positive. Okay, this is by the fact that the characteristic polynomial is stable. Now, since A is a constant matrix, since A is a constant matrix, so the solution must satisfy the it's not clear, right? All right, must satisfy the relation xt is equal to phi t x naught plus 0 to t phi t minus s f s xs ds. Okay, so if we take norm both sides of this equation, so what we have, taking norm on both sides, we have norm of xt that will be less than norm of phi x plus 0 to t a norm of phi t minus s f s xs ds. Okay, and then we can use this. We can use that norm of phi is less than re to the minus alpha. So we have, and so we have xt less than, that's phi, so we have r, and then I can multiply the e to minus alpha to the both sides of the equation. So I got here minus alpha t. Okay, so what left on the right side we have r, and then we have x naught here. This is x naught, sorry. We have x naught, so we have x naught here. Okay, plus that integrate 0 to t. So for that we have re respect to variable t, in this case alpha s, respect to variable s. So we have alpha s, then we have f s x s ds. Okay, so the first relation and second relation certainly valid for any t, for t any interval. This relation valid for t that for any t for which we have norm of xt less than some number a. So if we assume x naught, norm of x naught less than that a. Okay, so from the condition 2 where the limit tends to 0, so you can use the definition of limits from condition 2. From condition 2, given any m positive, we can find d positive such that for t positive and norm of x less than that number d, okay, we have f tx less than mx. Okay, this part here come from, if you look at the condition 2, we have f t x over x. Okay, we take a limit, those x goes to 0, then we need this goes to 0. So if this f, we consider this f t x, that one less than m, you can just multiply norm of x, just come. So we have this, that. Okay. So if we assume, the x naught less than d, then by the continuity of x, then by the continuity of xt, there exists, or you can find a number t1 positive such that norm of xt less than d for t1. Okay, this is the standard definition for the continuity. And therefore we have xt e alpha t. This is from the previous notes, my previous notes here. Okay, we use here that equation, now the inequality. This is less than r x naught plus 0 to t m r e alpha s xs ds. For t in 0 to t1. Okay, then you can use what we call Ground inequality, by Ground inequality, Ground inequality. You can search, you can find those things. What is the Ground inequality? Then which give the relationship between the norm. I mean, that's involve integral. Okay, so we have xt less than r x naught e m r minus alpha t, for t in 0 to t1. So what we are looking for, we want to show that the norm of x less than some numbers. Okay, so for that we may choose, so therefore we may choose m such that mr less than alpha and x t0, this is x naught, so that the norm of x naught less than d over 2r, which implies from here, we have the reason is that we want to show that this norm of x less than some numbers. So if you substitute all these things in there, the choice of that we made in there, so we have this thing less than xt less than d over 2 for t in 0 to t1. Okay, So since fx is defined, since fx is defined, since ftx is defined for x less than a, a norm of x less than a, and t between 0 and infinity. So this implies that we can extend, so this implies that we can extend the solution xt, which exists locally at every point of tx, the solution xt at tx, for t positive and x less than a. So if you have this thing, so it preserve that bound. So if x with this situation, x with this situation, we preserve that the norm bounded by that number. Okay, hence given any solution, given any solution xt, xt0 x naught with x naught less than d over 2r, then it is defined, on 0 t infinity and satisfies x t naught x naught less than d over 2. And if we make it d as small as we want, if we make it d as small as we want, so I can write d tend to 0, I mean as small as we want. Okay, so this will imply that this xt equal to 0 is stable. Is stable, and we have n mr less than infinity. This implies that the solution that x equal to 0, and the solution is asymptotically stable. Okay, so this theorem ensures that if we have the nonlinear system of this form, ax, atx, just a minute. Okay, atx plus ftx, this nonlinear system, and if a is constant, if a is just a constant matrix, then the isolated critical point 0, 0 will have the asymptotically stable. We guarantee that the solution is asymptotically stable. So when we were given the system, nonlinear system, what we need to check for the stability of the solution, first thing, just look at A. If A is constant, then we may jump to the conclusion that the solution is asymptotically stable. Example I have given before this theorem. Alright, so I think with the proof of that theorem, as well as some condition on the stability and condition on the function, the linearity, non-linear parts of the right hand side of our system. Okay, so I stop here for this video. For the next video, I'll give more example. All right, thank you.